Hey, hello there. Today's Leetcode challenge question is coin change 2. It's a dynamic programming question. So let's talk about this question. We have a few different type of coins that we can use to sum up to a certain amount. Each type of coin definitely have a different value. Well, for this question, we want to write a function to compute the number of combinations we can use those coins to sum up to that amount. So we are only looking at combinations. We're not looking at the sequential order of the coins being picked. We may assume that we have infinite number of coins for each kind. The examples, let's look at the one. We have a total, that's 5, and we have 3 type of coins, 1 to 5. There are 4 unique combinations of the coins we can do to sum up to 5. Single 5, 2 2, single 1, 1 2, and 3 1, or 5 1s. So that's the 4 different distinct ways of combine the coins we have to sum up to 5. The order of, if we consider some combination that involves 2 different types of coin, we can do 2 2 1, but there is no, but 2 1 2 is not considered as one unique combination. The order does not matter. So yeah, it's important to have that in mind when we reason about the subproblems. So let's talk about, let's look at this a little bit more graphically. The initial problem for the example is that we have to make up to 5, and we have 3 different coins, 1 to 5. So one may attempting to divide this into 3 different subproblems. If we choose 1, so the total reduced to 4, we still have those 3 different types of coin at our disposal. We reduce this total by 2 if we choose coin 2. The total reduced to 3, and we still have those 3 different coins. Or we reduce the amount to 0 by choosing a single 5. That's if we try to set this 3 different subproblems to sum up to the original parent problem. There will be seriously problem for this. Here we choose 1, here we choose 2. What if we choose another 2 and choose 1 to reduce this total to 0? So here will be 1. And on this branch, if we choose continuously choosing 2 from now on, after choosing the initial 1, this big reduced to 2 and now 0. So the problem with setting the subproblem to be only reducing the amount but not limiting the options of the coins is that we're going to have 2 to 1 and 1 to 2 counted separately. So we are basically double counting. And in this case, we actually, in this setup, we actually implicitly can actually thinking that assuming that the order of coins being picked does count as a unique way, but in fact for this problem it's not. So there's a problem in this subproblem setup. So what's the correct way of doing that? So let's say that we are picking 2 and reducing the total to 3. In the other branch, we will actually want to eliminate the option of choosing 2, because whatever the combination that involves 2 is going to be the subproblem from that branch and on. From this other branch, anything that if we continue to have 2 as an option, we're going to have overlap with the other branch. That's illustrated by this here. So for the correct subproblem setup, we're gonna, for one of the subproblem, we reduce the amount using the option. The other branch, we're gonna eliminate that options altogether. So that's the correct way of setting up the subproblems. So just make this a little bit formularically. We have an amount, we have some options. So one thing we can do is to have the amount intact and just pop out one of the options, and the other branch is going to be the amount subtracted by the last options. the order of the options being popped out really doesn't matter. Just for convenience purpose, I'm putting it as if we're removing the last one, or we can remove the first one too. So the problem basically being broke down into two subproblems. The first subproblem is the same amount, but with one less option. The second subproblem is that we reduce the amount by the first option. By the first option, this has to be in line with the one that's being popped out. So if we pop front, we have to reduce the amount by the first option, by the front coin's value, and have the options intact. So that's this transition formula. The base case is going to be if we don't have any amount, the amount is 0, we return 1. That means we successfully reduce the amount into 0. So we find one combination. So that's the base case. So whatever the options we have, that's going to be 1. Or we still have some amount that's greater than 0, but we run out of options. Let's just use an empty set here to indicate that. Then we want to return 0, meaning that it's not feasible. So there's no not 1 but 0 combinations through this searching. So that's the base case. All right. What else? Run out of the choice, or another one. If we just choose one options, that's just so happen to reduce the amount to be negative. Whatever the options we have remain, it's going to be 0 as well. So that's the 3 base case. So I'm gonna just code this top-down version, recursive version, using some lazy man's memoization method in Python. Just call this make change. We have an amount, and we are using an index instead of actually popping coins. So this I here means we consider coins index I and on towards the end. So that's effectively popping out the first one. The reason for that is I want to use LRU cache. So to using this, the arguments to the function has to be hashable. So I think list is not. So that is why I'm using an index to indicating what options has been eliminated in using this according to this formula. So just gonna copy this function, this transition function here, translate that into code. So the first branch subproblem is the same amount, but with one less option. So that's I plus 1. The second branch is make change. Amount subtracted by the first available coin that's currently in our at our disposal. So it's coins I, and have the I to be the same. Still have all the options from I and on. So that's the recursive relationship with the transition function. And we're just gonna put 3 different base case here. So if amount, oh sorry, I don't need this. It's not. The other one actually can be combined. So this is run out of the coins, so eliminated all the options of coins, or amount is less than 0, return 0. So that's just to use this function to calculate the requirements. We're gonna pass in the full amount, initial amount, and saying that we consider all the options from 0 and on, so all the options. This cache is going to handle whenever it's calculating some arguments and actually return a number. It's going to cache that combination, so putting this 2 as the keys, and so that later on when doing the recursive call, it's going to use the already cached value. So that's lazy man's memoization in Python. So let's try to see if it works. Yeah. Alright, so this is the top-down approach. The tricky part is to have the correct subproblem setup. It's important to realize the sequential order of how the coins are picked does not matter in this case. If that sequential order actually matters, the problem is much easier. So all we have is the amount subtracted by the option. Just for how many options we have, we break that into how many branches. That would be this naive kind of a setup. It will be an easy level question instead of this one. This one is a medium. So let's talk about how we do this from the bottom up. If we analyze this recursively, the transition function, it's a two-dimensional one. We have the options and the amount. So let's just say that the options are so the amount is the rows, and the options is the columns. Note that based on this transition function, we have the options pop front. That's basically saying that we are looking at a previous row. Sorry, options is the column, previous column, and the same row. Here is the same column, but some previous rows. So the immediate previous row. So we're dropping one of the options. Here we're dropping, we're deducing the, yeah, it's the same column, previous row, some previous row. Here is the previous column, same row. So we notice that this is actually can be compressed to be a single DP, single one-dimensional DP. It's not, even though it has two options, but all that here is the the same column, some previous row, or the same row, previous column, immediately previous column. So it's it can be space optimized using a single 1D DP. So instead of doing the 2D table tabulation, I'm just gonna do a one-dimensional. If we consider about the relationship here, it's additive. So it's not taking min and max and anything. So we actually don't need to store the previous column. All we need to do is just work row by row inside this column, and just adding the number, and that would be done. So we work this column by column, so calling value by value, and for each value we're looking at the different amount and just add the number based on this formulaic. So that would be the solution. Yeah, so let's do this. Actually, to reason about this, I think we could just transpose that so that it become a little bit more intuitive when we reason about that in 1D. So let's just use a row as the yes, we're gonna keep a row, but it's gonna be rotated to be a vector array. So the base case is going to be here. 0 is 1, and everything else is 0. So row is the amount, so we have 0 to the total amount. So that's why I'm transposing that to have that here. And we're just gonna doing that column by column. So if I'm gonna go beyond the actual amount, I should break. Otherwise, I'm just gonna go ahead and updating that. So this is pretty much just function of amount is equal to function of amount subtracted by the coin value and that. So it's this, but we are doing, instead of the subtraction, we are doing the addition. So it's kind of a reversed. This is top down. This formula record is basically the bottom up in the reversed ordering of how this works. We are not adding another second term because that second term is going to be handled in the next iteration for different type of coin. So that's that. For the return, it's just going to be returning the last item there. So let's see if it works. Okay. Try submit. Okay, working too. So yeah. So that's converting from top down to bottom up. We analyze this here. We realize it's even though it's a 2D, but we can compress that to be a single one-dimensional. So the way to think about this is going to be handled by the previous iteration over the coins, and this one is going to be what we handle for this particular coin here. Alright, so that's this question today.